So we are very fortunate to have Daniel Siegel from Columbia University to talk a little bit about Collapsars, which basically is a new model to generate R process elements, and this model is believed to have resolved some key issues that neutron-star binaries have with respect to R process enrichment of the galaxy. So this is the model that Dan and Jennifer Barnes and Brian Metzger have put forward, and we can't wait to hear more about this model. So Dan, please, you can start the talk. And you should unmute yourself so we hear you.
Okay, so I hope everyone can hear me well. Thanks so much, Mohammed, for the invitation to the seminar series, and thanks to everyone for attending. Yeah, so I'm gonna talk about the Collapsar scenario that, as Mohammed mentioned, Jennifer Barnes, Brian Metzger, and I have sort of proposed fairly recently. But I'll sort of try to embed this in a little broader context. And so I'm also gonna talk about neutron-star mergers, because that is how the story started and how we got into looking into Collapsars. So to begin with, let me sort of try to summarize the entire talk essentially in terms of a conjecture, namely that outflows from compact accretion disks synthesize most of the heavy R process elements, and by heavy R process elements I mean essentially beyond second peak. So in more concrete terms, so the kind of systems that I'm thinking of here are neutron-star mergers, of course, which are associated with short gamma ray bursts. And on the other hand, the other types of systems that I'm thinking of are collapsars, which are associated with long gamma ray bursts, and also accompanied by DRB supernovae, observationally known as broadline type 1c supernovae. And so I'm going to talk about essentially both systems. The first one, neutron-star mergers, is at least sort of a system that we have at least one concrete and direct observation of so far, namely the beautiful kilonova that was following the GW170817 event. And just to remind everyone again, so this is essentially a plot that summarizes 650 individual flux measurements from different groups taken with different telescopes, put together and sort of jointly fitted by kilonova models. So you can see here that essentially there was a sort of early blue emission, essentially peaking on a time scale of a day or so, and sort of this red component peaking on a longer time scale of several days, so a week or so, and peaking in the infrared. So fitting essentially these kilonova models, this data with kilonova models, essentially the typical parameters that different groups got are listed here on the left side. So for this blue emission, that seems to be well fit by an ejecta mass of something like 1% of a solar mass or so, moving at fairly high speeds of say 20 to 30% the speed of light or so. This early peak time scale was indicative of sort of a fairly low opacity. That requires sort of a negligible Lanthanide fraction to be present, which again then translates into an electron fraction of fairly high, or comparatively high electron fraction of at least above 0.25 or so, with sort of 0.25 being some of the, essentially like a critical threshold for lanthanide production under typical circumstances. So just to remind everyone how we get blue and red kilonova components. So the critical thing here is really that it depends on the outcome of the R process. So in case that no lanthanides are produced and you end up essentially with an iron peak composition or so, those opacities essentially would typically produce a sort of rather blue transient peaking on a day time scale or so. So lanthanide-free, low opacity, high YE, sort of blue kilonova transient peaking in the optical. And instead, if the R process goes all the way beyond the second peak and produces lanthanides, then even a tiny amount of lanthanides present in this outflow can substantially boost the overall opacities of the material and then sort of move the transient into the near infrared, peaking on later time scales, and also making it dimmer. So it's a lanthanide rich, high opacity, low YE infrared, or say red kilonova transient. So in this red composition, so this red transient was essentially indicative of even more ejected mass of at least a few in 10 to the minus 2 solar masses, although there are, of course, significant error bars and systematic uncertainties to this. But something on the order of 10 to the minus 2 solar masses or so, moving at slower speeds, typically something like 10% the speed of light, and sort of peaking at later times, and in the infrared then sort of required at least some non-negligible lanthanides being produced in that outflow. That again then translates into a fairly low YE outflow, which needs to be explained sort of by neutron-star merger ejecta. So trying to sort of make sense of these observations, we have to look at essentially the neutron-star merger phenomenology. So what kind of ejection mechanisms do we have at hand in order to explain these types of ejecta? And I'm pretty sure that many of you have seen this many times before, but so just to make the story complete, we have on the one hand black hole neutron-star mergers, which I won't focus on too much for this talk. And so let's concentrate on the neutron-star mergers in the context of GW170817. So depending on the equation of state and some other binary parameters, typically mostly the total mass of the binary system, we can either have a prompt collapse to a black hole surrounded by only a very tiny fraction of material that circularizes around the remnant black hole, or we can essentially form a at least metastable neutron star that lives for some time, tens of milliseconds to hundreds of milliseconds, maybe even longer, so referred to as a supermassive or hypermassive neutron star that then eventually can also collapse to a black hole surrounded by some massive accretion torus, or it can form sort of a much longer lived object, maybe even a stable neutron star, which is still an option on the table and would be a very interesting and very fascinating sort of discovery in the next couple of years. So in this complex phenomenology, there can be many mechanisms at place that can give rise to ejection of neutron-rich ejecta that can undergo the R process and produce kilonova emission. The earliest types of ejecta mechanisms that have been already discovered back in the 90s with the first SPH simulations is dynamical ejecta, tidal ejecta that comes essentially, the tidally ejected material that leaks out of the outer Lagrange points of the system during the very final and spiral phase. There can be a second component of dynamical ejecta called sort of shock-heated ejecta that originates from the contact interface of the two neutron stars as they touch, where a strong hydrodynamical shock forms and sort of pollutes the environment with a lot of baryonic material in a almost sort of spherical way. So if we don't end up in this prompt collapse scenario, but instead form at least a metastable object for some time, there are two additional components of mass ejection, two additional mechanisms, namely by winds from the surface of this remnant. These winds can be either driven by neutrinos or by magnetic fields, or a combination of both. There can be neutrino-driven winds in a fairly similar fashion as in ordinary core collapse supernovae, or there can be winds driven by the amplification of magnetic fields in the interior of this remnant that gives rise to magnetic field gradients that drive material from the surface. And finally, something that we've looked into in a lot of detail recently are these post-merger accretion disks where material circularizes essentially in a massive accretion disk around the remnant, and thermal winds give rise to significant mass ejection from the system. So just giving you a few more details and trying to connect this to the kilonova of GW170817, this tidal ejecta is the one that is launched first, even during the late in spiral. You can see here these nice sort of spiral patterns. This is typically very cold a material that is very neutron rich, so very low YE, and is typically moving fairly fast, say 20% the speed of light or so. So this would typically give rise to what we would call a fast red kilonova transient. If we look at the shock-heated ejecta, the other part of the dynamical ejecta, that comes from this contact interface, is shock-heated typically to something like tens of MeV. So this is very hot material where weak interactions already set in and dramatically change the composition of the material. So this typically gives rise to material that has a fairly high YE of typically a mean YE of above 0.25 or so. So this would, taken just as a separate ejecta component, would essentially give rise to a fast blue kilonova transient. So in terms of these winds, we have the following situation. So for the winds from a remnant, they are typically fairly slow, so something like 10% the speed of light at most. Of course, those are very hot. They come from this very hot shock-heated remnant. So typically, especially if the winds are mostly neutrino-driven, the mean YE will be actually fairly high due to absorption of a lot of neutrinos that raise the electron fraction above this critical threshold for lanthanide production. The same case in the magnetic field situation, simply because there's a lot of neutrinos around. So this would, in principle, give rise to something like a slow blue kilonova transient. But there are ways in which these neutrinos and magnetic fields could potentially act together to conspire, essentially, to give rise to a qualitatively different phenomenon that was also recently pointed out, where in principle, these magnetic fields can, if strong enough, can further accelerate the outflow and give rise to more ejected mass in total and also to higher speeds. So in principle, if they act together, one could also envision to have something like a fast blue kilonova transient. Now, if I compare these sort of typical ejection mechanisms from numerical relativity simulations with the typical parameters inferred from the GW170817 kilonova, we get the essentially following picture. So here I've just plotted the ejecta velocity as a function of the ejected mass, taking sort of different, taking a compilation essentially of different neutron-star merger simulations from different groups over different years with different codes, including SPH, including grid-based numerical relativity codes, using a huge variety of different equations of state and mass ratio. So to essentially sample the parameter space as much as possible. And as you can see, essentially, typically, the dynamical ejecta channels and including some of the post-merger winds actually cluster essentially around here, and sort of in principle inconsistent with these sort of parameters inferred for the red component of the kilonova. So that part of the emission that seemed to have produced the Lanthanides in this recent event, even if you account for very generous error bars to take into account systematic uncertainties and these kind of things. So to me, this sort of clearly points away from dynamical ejection mechanisms. So there essentially has to be something else, and that brings me to discuss the post-merger accretion disks, where essentially the imbalance of viscous heating in this accretion disk due to MHD turbulence is not offset by neutrino cooling of the midplane of the disk. So at higher latitudes, I can actually let this movie run. So at higher latitudes, essentially, heating dominates and drives thermal winds from what we call a hot corona. And these winds are further accelerated by something like a nuclear rocket effect, where essentially the free neutrons and protons from that disk eventually recombine into alpha particles and heavier seed particles for the R process, and thereby release a lot of nuclear binding energy that becomes available as specific enthalpy that further boosts the flow and accelerates it typically to something like 10% the speed of light or so. So looking into this in a little more detail, we essentially find that these post-merger accretion disks sort of naturally provide all the conditions that we need to explain for this for the red kilonova emission in GW170817. So in particular, what we need to explain is the neutron richness of these outflows. So how this outflow can actually produce second to third peak R process elements. And this turns out to be due to very interesting physics that happen in these accretion disks. And I'm going through this now in a little more detail because essentially the same physics applies to the collapsar scenario. So in the inner parts of the disk, the accretion rates of onto the black hole are high enough, so the central densities are fairly high that you essentially force the electrons to become degenerate. And under these degenerate conditions, the weak interactions, meaning electrons and positron capture, are changed because positron formation is heavily suppressed. So this favors essentially electron capture onto protons to convert protons into neutrons and provide neutron-rich conditions in the interior. And there's also actually a self-regulation mechanism at place that keeps it exactly at mild electron degeneracy. So essentially, this is very interesting because in this way, the system completely forgets its initial conditions. So there's a reservoir of essentially neutron-rich material in the interior of these disks that continuously feed very neutron-rich material into these outflows to keep the overall electron fraction of the outflows low enough so that lanthanides can be actually produced. And so if we compare if we sort of post-process all these outflows through a nuclear reaction network, we can actually explain essentially the formation of R process elements all the way from the first to the third R process peak. So this nucleosynthesis looks in a little more detail like this. So this shows a movie of just a single fluid element. So some of you may have seen this already in some previous talk. Essentially, if I plot here the proton number versus neutron number, I just follow a single fluid element that is ejected away from this disk into outer space. As it undergoes the R process, we get essentially the following picture. So these are results obtained by Jonas' Skynet code. So we start essentially at in sort of a little bit off the disk midplane with this fluid particle. So as it cools down and goes through the corona, we produce these seed particles, stable isotopes at the center of the valley of beta stability. Now, at some point, so there's some oscillations here because of the turbulence in the corona. So now, once we sort of hit the critical threshold of a few gigakelvin for nuclear statistical equilibrium to break down, we start the neutron capture reactions and now sort of move off the center of the valley of beta stability to form fairly heavy neutron-rich nuclei and now we run out of free neutrons. And all these isotopes have to decay back to stability, and this is exactly what powers the kilonova. And a very similar picture actually applies to these collapsar outflows. So there's a lot of analogy here. So these outflows are fairly slow. As I already mentioned, you can see the velocity distribution here in the bottom left. Typically something like 10% the speed of light. And we find very massive outflows. These MHD-driven outflows seem to be fairly powerful in actually evaporating the disk, so that essentially 30 to 40% of the initial disk mass is actually unbound, and only say something like 60 to 70% or so is accreted. And if we look at the typical outcomes of binary neutron-star merger simulations, we get typical accretion tori of something like 10 to 20% of a solar mass if there's no prompt collapse. And this translates into an unbound ejected mass of at least 10 to the minus 2 solar masses, which is exactly the mass scale that is needed to explain the red kilonova emission. So taking sort of GW 170817 and the sort of interpretation in terms of disk outflows and the total ejected mass inferred from that event, in principle, one can explain the total amount of R process material in the galaxy, although admittedly there are of course a lot of uncertainties. But there are other ways if we don't look into at the actual sort of rate yield constraints and the total amount of ejected material and the total amount of R process material in the galaxy, but at the sort of temporal assembly of our process elements in the Milky Way, then there are actually a few challenges for neutron-star merger models, or for models that only rely on neutron-star merger enrichment, which I'm now going to discuss in a little bit detail, and I'll contrast this with the Collapsar scenario in just a couple of minutes. So I'll just to remind everyone of some very basic anatomy of the Milky Way. So I'm going to talk about the thin disk and thick disk stars in a little bit, and also about the halo. So stars in the dispersed stars, essentially in the stellar halo, but also in globular clusters and in dwarf galaxies. So just going very briefly over some of these challenges. So one open question still is whether or not neutron-star mergers, due to their delay time with respect to star formation, are actually able to explain the very early prompt enrichment of our process elements seen in halo stars at fairly low metallicity. So this shows a plot from a paper by Van der Voort et al. Looking at our process enrichment versus relative to iron. So these are is in abundance space. These are logarithmic units calibrated with respect to the sun, and as a function of metallicity here, which essentially at late times becomes an indicator of time. And so some of these more detailed cosmological based, so cosmological simulation based enrichment models still show some problems explaining sort of the high level of enrichment at very low metallicity, around -3 and lower. Although there have also been other results that essentially claim that this early enrichment can be obtained even if neutron-star merger delay, realistic neutron-star merger delay times are accounted for. But still, it seems to be somewhat, at least, of an open question. And maybe there may be other ingredients needed to explain the full story, meaning the hierarchical assembly, for example, of the Milky Way halo from subhalos, and taking also into account potential cross-pollution between different subhalos to account for very early enrichment. Another challenge that neutron-star merger models potentially face is the following that comes from dwarf galaxies, related to very strong observed R-process enrichment in some of the ultra-faint dwarf galaxies, such as Reticulum-2, and there's been also a recent second ultra-faint dwarf galaxy observed where in some of the stars strong enhancements of europium were found. One problem with these ultra-faint dwarf galaxies is that they have very shallow potentials and so very small escape velocities. Now, neutron-star systems always get kicks through their supernovae, so one essentially has to explain neutron-star merger systems with less than 10 kilometers per second, or say on the order of 10 kilometers per second kick velocities, and also fairly short merger timescales, because simply the star formation period in these ultra-faint dwarf galaxies is fairly short. So based on the galactic binary neutron-star distribution, it has been argued sort of empirically that in principle this is not impossible, so this can be accommodated for, but the merger timescale really critically depends on the initial separation and can sort of lead to qualitatively different outcomes depending on what assumptions are made for this initial separation. Based on population synthesis modeling, it has also been recently proposed that in principle a very specific channel of binary stellar evolution can give rise to ultra-compact binary systems if one invokes this a second phase of common envelope evolution during the binary phase referred to as the so-called unstable case BB mass transfer that could end up with a binary as close as 0.1 solar radii in separation that could then sort of lead also to fairly prompt mergers. Another potential challenge relates to globular clusters. And arguably the situation here could even be more constraining because these globular clusters have even much shorter star formation periods, something like 10 megayears or even shorter than this. So this would imply extremely short merger timescales. Or another idea, a way out of this was that essentially one could conceive of a second period of star formation at later times. So the first star formation period goes off and all the supernovae essentially blow off most of the material out of the cluster. And then on a longer time scale, winds from AGB stars on the asymptotic giant branch, those winds could enrich the intercluster medium with new material from which a second generation of stars could form. That would give, that would sort of alleviate some of the strong requirements on these short merger timescales to at least 100 mega years or so, during which neutron star mergers would then have time to enrich that intercluster medium with R-process enrichment so that it can get into the second generation of stars. Now moving from the halo essentially to the galactic disk, if we sort of look at the europium, so the assembly of europium in the galactic disk over time, we essentially get the following picture. So what I highlighted here are the disk stars. So the stars in the Milky Way disk shown here as these cyan dots. And you can see that there's a clear trend at sort of late times, at high metallicity, where europium versus iron, this sort of negative slope of the europium versus iron trend. This has been noted before a couple of times. And the problem here is that neutron star merger models actually have a hard time explaining this negative trend. The problem being that neutron star mergers, as well as type 1a supernovae, which produce most of the iron at these late times, follow essentially the same delay time distribution with respect to star formation, which goes as t to the -1. And these two delay time distributions essentially cancel each other. And so at late times, you get essentially a flat trend or even a moderately rising trend. But it's actually very hard to explain sort of this negative trend at late times. Another problem that I just realized essentially 1.5 weeks ago is the following. If you look again at the disk stars and you look at the production of europium versus magnesium, so the production of R-process elements, heavy R-process elements with respect to alpha elements, there's also a problem here that essentially, again, europium lags behind the alpha elements in the merger models. And so it's very hard to explain sort of a positive europium versus magnesium values at low metallicity that sort of then gradually transitions into a negative trend at late times again. Sort of essentially, neutron star merger models would more or less, at least in very simple sort of chemical evolution modeling, would predict and sort of continuously rising trend until late times. So this essentially is a summary of potential challenges for chemical enrichment just based on neutron star mergers. And this brings me now to discuss collapsars. So just to sort of remind everyone what these systems are, these are essentially rapidly rotating massive stars that collapse at the end of their lives into what is called either a failed supernova explosion, which would be a direct collapse into a black hole, or a weak explosion where essentially you first form a proto-neutron star and you can have a supernova, potentially MHD-driven supernova at early times. But then sort of at some point, the proto-neutron star collapses under the fallback material to form again a black hole that is then surrounded by an accretion disk. And these massive rapidly rotating stars have enough angular momentum so that material essentially just doesn't radially fall into the black hole, but due to the angular momentum actually starts to circularize around the black hole to form a massive accretion disk. And this has been sort of a widely accepted model also to explain the generation of long gamma ray bursts. This is the classical Collapsar scenario proposed by McFadden and Woosley back in the late 90s. So just to put this again in other words, one Collapsar scenario overview is the following, as I mentioned. So we have the collapse of a rapidly rotating massive star that can either directly collapse to a black hole and form, again, a black hole torus accretion system, or we can go through this sort of kind of either weak explosion or supernova explosion phase where we first produce a proto-neutron star and then sort of some MHD-driven, jet-driven explosion can power a GRB supernova, and can also potentially produce some R process elements, and before then finally collapsing to a black hole torus system. So we end up again in such an accretion system. So how do these Collapsar accretion disks actually work? Well, so in this upper left panel, I'm showing essentially the typical accretion history of such a Collapsar system. So the fallback of material from the collapsing star onto the center, the sort of innermost 1 to 2 solar masses typically don't have enough angular momentum and just collapse into a black hole. And then as you get to sort of outer and outer envelopes, there's more angular momentum and material starts to circularize. So this initial phase, once the accretion disk forms, is then sort of the gamma ray burst period, during which you have very high accretion rates that are able to explain sort of essentially the luminosities of long gamma ray bursts. And then at later times, eventually, as you get to outer and outer envelopes, the accretion rate then rapidly drops at some point. And so we've looked at these accretion systems in more detail with GR-MHD simulations, taking into account all the weak interactions. And we find that there's actually, again, very interesting physics depending on electron degeneracy, and which translates essentially into accretion rates and central densities of accretion disks. So if we start sort of inversely, starting from the low accretion rates at late times, there typically the accretion rates are fairly low, and weak interactions don't play too much of a role in the total energetics of the accretion disk. And ordinary stellar material is falling in with roughly equal numbers of neutrons and protons, and sort of the weak interactions are in equilibrium, so electron and positron captures roughly balance each other, and so the composition is not really changed, and the material therefore has essentially a YE of roughly 0.5, so equal numbers of neutrons and protons, and we actually find that these outflows synthesize nickel 56, which you can see in this as this green curve in the upper right plot. So at late times, essentially nickel-rich outflows, which is also what was originally found in the McFadden and Woosley simulation. But now if we actually follow the weak interactions more closely as you get to higher accretion rates, so in the early phases during which the gamma ray burst is produced, we actually find that the accretion rates are high enough so that, again, the disk becomes dense enough so that electrons become degenerate, and under these degenerate conditions, positron, so pair production and therefore positron creation is heavily suppressed, which then favors electron captures onto protons. So we sort of favor the upper reaction and convert protons into neutrons. And this is exactly the process by which you sort of convert the ordinary stellar material into something that is neutron-rich in the inner parts of the accretion disk. So with this moderate electron degeneracy, we again sort of find low YEs of 0.1 or so that is sufficient to produce heavy R process elements. And so you can see if we again compare the output of nuclear reaction network calculations, again with Skynet here, to solar abundances, we actually get an abundance pattern that fairly nicely sort of follows the solar abundances and does produce second to third peak R process elements. Now, sort of from these sort of first principle simulations and calculations, accepting that we know that such accretion disks can produce R process elements, the relevant question then, of course, to ask is how much can we actually produce in these collapsars? And so admittedly, of course, there's a lot of uncertainty, and we can sort of try to approach this question from at least 3 different angles. So there's one purely empirical argument to be made, just comparing essentially long versus short GRBs, which are observationally sort of characterized fairly well, and we know their rates fairly well. So the assumption here is essentially that the R process material produced in these events is created from outflows of these accretion disks, either in the post-merger accretion disks in the case of short gamma ray bursts, or in Collapsar accretion disk in the case of long bursts. So the total amount of R process material is then proportional to the accreted mass onto the black hole, at high enough accretion rates, and then multiplied essentially by how frequent these events are, so by the rates. And so we can estimate, so plugging in sort of observational numbers for this, translating accreted mass into isotropic gamma ray luminosity, we obtain that collapsars should contribute a factor of at least 4 to maybe even 10s more than neutron-star mergers. So this would sort of be already a first hint or indication that collapsars could actually be the dominant contribution to the galactic R process. Now, a second essentially empirical argument is essentially integrating over the whole star formation history of the Milky Way, and then asking how many collapsar events do we think the Milky Way had, and so how much material, R process material, does a single collapsar event has to produce in order to explain what we see in terms of total R process. And so this is the essentially second estimate, and then sort of again putting in observational numbers, we find that at least a few percent of a solar mass, up to tens of percent of a solar mass, has to be produced per collapsar event, if collapsars would be sort of the total or say dominant contributor to the galactic R process. And dialing in essentially the total amount of R process material produced in a merger event, assuming that GW17 or 817 is a typical event, that estimate is actually consistent with the first estimate. Now, and then finally, there's of course also a just purely theoretical argument to be made, just based on the simulations and on pre-supernova stellar models. So just integrating over the fallback history, over the accretion rate and the fallback history of pre-supernova models, and then sort of dialing in what we know from the simulations of how much material we think is ejected into winds. And so going again over many of these pre-supernova models, we find a huge range of potential R process masses, all the way from a few in 10 to the minus 2 solar masses up to, in some cases, maybe even up to 1 solar mass of R process material, which again is a fairly broad range and consistent with the first two estimates. So it's fairly intriguing that essentially all these 3 estimates are roughly consistent, but admittedly with large error bars. Now, if we look at the total production of R process elements again, and compare neutron-star mergers to collapsars, we get the following picture. So this just shows the constraints on the total R process mass in our galaxy, sort of broken down again into this degeneracy of ejected mass versus event rate. So this sort of rate yield degeneracy. And so I'm plotting here essentially different constraints on R process production that we have in the Milky Way. So the yellow band essentially indicates constraints from plutonium measurements in the deep sea crust. These contours highlight constraints from dwarf galaxies, ultra-faint dwarf galaxies, but also other dwarf galaxies. The overplotted on the left-hand side is the binary neutron-star merger rate from LIGO. Then the inferred ejecta mass from the kilonova following the GW17 or 817. And in the horizontal bands, you can see the typical ejecta masses that we get from neutron-star merger simulations. And you can see that essentially all of these constraints kind of overlap and sort of neutron-star mergers. So assuming that GW17 or 817 was kind of a typical merger, essentially all these constraints seem to be consistent. And again, highlighting that a lot of mass has to be ejected in neutron-star mergers, and the only way so far that we think this is possible over a large parameter space for neutron-star mergers is are these disk ejecta, so the post-merger accretion disks. For collapsars, we get a similar picture, but that arguably may even better fit the existing constraints. As you can see here, I've overplotted along on the right-hand side, a long GRB rate that is corrected for beaming. So that's the intrinsic rate. Also overplotting the typical collapsar disk ejecta that we get from these previous 3 arguments. And you can also see that they nicely sort of overlap with the existing constraints on R process enrichment on rate versus yield. So essentially, collapsars are something that are even a little more rare, but give a higher yield than neutron-star merger events. Now let's contrast. So moving away from sort of the looking at the total R process production in terms of rate and yield, let's try to confront this again with the time evolution of R process enrichment in the galaxy. So for collapsars, at least we don't have to worry too much about the first three constraints, simply because we don't need to worry about binary stellar evolution in this case. Collapsars just occur with negligible delay with respect to star formation, and they happen right where they were produced, where the stars were first born. So essentially, there may be other potential challenges, but at least we don't have to worry about these 3 points of producing R process, a lot of R process early on. And so looking at the disk stars, again, the R process versus iron evolution at late times, we actually get this nice picture that sort of dialing up the Collapsar contribution to the total galactic R process, and you see the percentages indicated here in the plot. So once collapsars become dominant, say something like 80% or so, we're sort of able to obtain this negative trend of europium versus iron at late times. And this doesn't come as a surprise, because collapsars, as I said, follow the star formation history faithfully. So and sort of collapsars following the star formation history closely just gives you a negative trend at these late times. So this is not a big surprise, but shows that essentially one could, taking sort of these observations of europium enrichment in disk stars and sort of more sophisticated chemical evolution models, one would be actually able to calibrate and infer a total collapsar contribution. So this would be just an empirical argument to say how much R process from collapsars we should have. And now if we compare this to the alpha element production, also for the same set of parameters, and of course admittedly these are very simple chemical evolution models, but just to sort of make the main point, again, if you dial up the collapsar contribution, one can also sort of nicely recover essentially this europium versus alpha element evolution at late times. Okay, so in the last couple of minutes, I'd like to just really briefly discuss of how can we actually test this collapsar scenario observationally in the future, or potentially in the near future. So the challenge here really is that essentially we have something like a kilonova, like a giant kilonova, if you wish, in a supernova, and so we'd have to sort of disentangle these two things. So just if we look at the sort of heating of what provides the dominant heating to the transient, then at early times, the sort of decay of nickel into cobalt and iron from the supernova, from the MHD supernova ejecta, dominates the overall heating of the ejecta, and therefore sort of essentially determines the light curves and the spectra. However, at late times, this power law, T to the minus 1.3 or so from the R process, actually dominates, so at timescales of hundreds of days. So sort of if we concentrate at late times, then the dominant heating should actually come from the R process, and so there may be a sort of naturally there should be sort of a late time signature of the R process in the GRB supernova light curves and spectra at very late times and timescales of hundreds of days to years. Now, can we also have signatures that are earlier? So how, can it actually affect the supernova light curve at early times, maybe even at peak light? And the answer is probably yes. And it depends on how much R process material. So the way of how this R process material can influence the supernova is through supplying additional opacity that comes from the heavy R process elements from the Lanthanides. So it depends on how the Collapsar ejecta, the disk ejecta, sort of mixes with the supernova ejecta that has been launched earlier. So in the case of a typical sort of collapsar scenario where the disk winds come out at late times and the supernova has already gone off, these R process winds should actually not interfere too much with the supernova ejecta. There may be some mixing, and we are actually looking at this in a lot more detail right now with detailed hydrodynamical simulations. But assume that there's sort of little mixing for now. And then Jennifer Barnes did nice calculations of radiation transport calculations of such a sort of R process and supernova outflow. And in this case, if there's little mixing, we can nicely actually recover the typical supernova, GRB supernova light curves as we know, with the typical broadline features shown here on the right with the solid lines. Also in dotted, you see as just a rough comparison, the typical sort of GRB supernova as the supernova 1998 BW. However, in the other extreme case where there is like a lot of mixing, there's sort of maximal mixing, which you would in principle expect for an MHD-driven supernova. So if the jet that unbinds material and actually makes the outer layers explode and form the supernova, if that jet actually produces R-process material, heavy R-process material, lanthanides, that material will be inevitably mixed into the outflow. So there would be essentially full mixing. So even if the jet produces only a tiny amount of R-process material, say 10 to the minus 3 solar masses, or even a little less than that, that material would already supply enough opacity to the nickel 56 rich supernova ejecta that the light curves and spectra would be affected in a way that would be inconsistent with existing type 1c broadline supernova light curves and spectra. So you can see this here in the plot as the dashed line. So essentially the supernova at peak light will be much dimmer, the peak will be broadened, and also the peak will occur at later times. And also the broad-lined spectra, as you can see, are shifted towards the infrared and would be sort of inconsistent with typical type 1c supernova light curves. So in principle, there's of course more detailed study needed here, but in principle, this would indicate that one could, in principle, rule out the contribution of MHD supernovae to lanthanide production based on GRB supernova light curves and spectra. And so since time is up, I should wrap up here and finish with some conclusions. So I was trying to argue that essentially these massive post-merger accretion disks in neutron-star mergers are expected to be a ubiquitous phenomenon. So potentially many of the future mergers actually may show such slow and massive red kilonova transients. Disk outflows can, in principle, synthesize the entire range of R-process nuclei from the first to the third peak. And so, as I mentioned, should overall, seen as a population, sort of dominate the neutron-star merger ejecta as a whole. But that is something that will be very exciting to test in the next couple of years with more LIGO events. So as I mentioned in particular, the GW17 or 817 sort of red emission seems to be naturally explained by such outflows from post-merger accretion disks. In Collapsars, fairly similar physics actually applies, and the sort of overall lower event rate of Collapsars with respect to mergers is overcompensated by the higher yield that you get per Collapsar event, so that Collapsars could dominate the overall production of R-process elements. And there should be direct observational imprints of such R-process elements in the GRB supernova light curves and spectra. But sort of more theoretical modeling is needed here, but also we have to hope for a very nearby GRB supernova that is close enough so that we can follow it up actually at very late times to look for possible imprints of R-process nuclei in those ejecta. And finally, just to one last note and outlook for the next couple of years, what we can do with neutron-star merger populations. So, of course, one exciting question to ask and to investigate with the next couple of LIGO events is really to see how ubiquitous such post-merger accretion disks are. Do they really sort of dominate overall mass ejection? What are the sort of the merger rates. So I'm looking forward to shrinking essentially the uncertainties in the merger rates to see what actually the contribution of neutron-star merger to the total galactic R process will be in a sort of more precise way. Also, we need to know the contribution of black hole neutron-star mergers, which is also still a very open question. And sort of personally, I'm looking very much forward to seeing a lot of diversity among the mergers. So what are the contributions of other ejecta channels, of tidal ejecta, of very unequal mass systems, other contributions from winds, from the remnant neutron star or long-lived remnant neutron star, which could strongly boost the amount of light R process elements we have. Also, some of these sort of corner cases could shed light on, for example, what the origin of actinide boost stars are, which require very neutron-rich initial conditions. And also, in terms of the sort of observed scatter of light R process elements and the so-called diversity and universality of the R process, it will be very interesting with future events to sort of better constrain what the individual contributions from different nucleosynthesis sites really are. So the blue ejecta, for example, so the blue kilonova components, and therefore the light R process contribution to the R process from neutron-star mergers can vary by orders of magnitude depending on this very complex sort of phenomenology of neutron-star mergers. And that translates, of course, into a broad range of Lanthanide mass fractions of the final integrated outcome of neutron-star mergers. Also, one very interesting question will be whether or not there's actually a significant blue ejecta and therefore light R process components in black hole neutron-star mergers. And finally, also in Collapsars, there can be a huge variety among different events, simply because there's a huge variety of supernova progenitors. And depending on this progenitor model and the exact accretion history, so depending on the stellar structure and the exact accretion history, there can be, the light R process contribution can vary again by orders of magnitude, which again translates into different Lanthanide mass fractions. So this can also potentially explain, some of the scatter among the light R process elements that is observed in metal poor stars. Also, in the Collapsar scenario, there can be contributions to the R process from the MHD supernova, but for the reasons I explained, will probably be mostly on the light R process elements. And I think I should really stop here and take any questions you may have. Thanks.
Right. Who has any question? Please just unmute and ask your question.
Hi, this is Alex G. I have many questions, but I'll ask one. I guess the question I have is about neutron-star black holes.
Yes.
So I'm trying to understand if the degeneracy inside of the disk that happens in the Collapsar case is also happening in the neutron-star black hole, and thus would that, I guess, sort of affect whether or not it's only making the high YE or the low YE ejecta, if that makes sense.
Yes, yeah, really good question. Thanks. So yes, so the quick answer is yes. Also in the black hole neutron star merger case, there will be massive post-merger accretion disks. There's a lot of material that will be sort of tidally disrupted. So there may be actually a very strong sort of dynamical component, but there will also be sort of a very massive post-merge accretion disk, at least in those systems where sort of the companion, the neutron star, actually gets tidally disrupted. So this depends very strongly on the mass ratio of the system. So there's a huge part of the parameter space where actually nothing will happen because simply the neutron star plunges into the black hole and there's no ejecta at all. But in the cases in which we do have or do expect ejecta from black hole neutron star mergers, there will also be a significant component from this post-merger accretion disk. And there again, the accretion rates are very similar to the neutron-star merger case, meaning that also the nucleosynthesis signature from that should be fairly similar. So there will be light R process elements just as part of these as part of these outflows, but I would at least naively expect that sort of the heavy R process contribution would dominate. And the interesting thing about the black hole neutron star mergers is that it's actually very hard to generate other, or to think of other components that could be entirely blue and not contain any red components. So that would be interesting to see if we do see a kilonova from a black hole neutron star merger in the next couple of years. That there are very many interesting questions to answer with those observations.
Hi, Daniel. This is Jonah.
Hi.
So I have a question about your Collapsar models.
Mm-hmm.
In the how does the material actually escape, right? So are you imagining, or in your models, does the material sort of come out entrained by the jet, or is it similar to the merger scenario where you've sort of got this quasi-isotropic lobe of outflow?
Right. Yeah, that's a really good question. Thanks. Yeah, so it's probably a combination of both. So I mean, to be honest, so in these simulations, as you may have read in the paper, we don't do the fully sort of global simulations and take into account the whole star, and so we only focus on the accretion disk here. But in previous global simulations, at least in 2D, it has been essentially shown that these disk winds can easily escape sort of in the because the problem is not an entirely spherical symmetric problem, so sort of the infalling ram pressure of the material is not equal in every direction. Simply because of the angular momentum in the system. So what will preferentially happen in these systems is that material in the polar directions which has the least angular momentum actually pretty promptly falls onto the black hole and forms this initial black hole. And therefore sort of clears up a sort of more or less polar funnel in which also then the jet is able to escape. And it's really sort of in these more polar regions where also the disk outflow comes out. So in those regions, the ram pressure from the infalling material is actually much, much smaller. Material will actually mostly fall in onto the accretion rate, onto the accretion disk, and circularize on the accretion disk in the equatorial direction. So this is really where material, or where the outflow will be probably unable to escape from the system, and in fact an accretion shock will form there. But sort of in the sort of more polar directions, these disk winds can sort of escape from the black hole. So there's also, so I mean, this has been essentially shown by 2D simulations in the past. It depends a little bit on how powerful these outflows are, but in principle they can also. So in the paper, if you're more interested in that question, we've actually, in the revised version, it's not on the archive yet, but we've added a section with a bit more details on that, with some sort of more analytic estimates.
Cool, thanks.
You're welcome.
So could you tell us a little bit about the mass of the accretion disk that formed in the Collapsar, and is that are you doing any extrapolation to higher masses or from a lower mass simulation, or is it exactly the mass that you?
Yes, thanks. Good question. So let me just go back to this accretion history again. So on the slide here. So the accretion disk is essentially fed by sort of many solar masses of material that eventually sort of fall onto the equatorial plane, circularize, go into the disk, and become eventually accreted. So the disk is continuously supplied with material, and the actual extent of the disk then depends on sort of at what time you look at. So at what time in the accretion history you look at the accretion disk. So initially, if, things fall more into the center and circularize at sort of small radii, and then you sort of gradually go out, and sort of also the accretion disk is and the winds are sort of more able to push against the infalling ram pressure and to push out the accretion shock at larger radii. So what is important and so you can do, and this is what we've done, so you can look at the accretion history of many different progenitor models, which will give you very different sort of accretion histories, different accretion rates, sort of different temporal durations for these high m dot and short gamma ray burst periods. what is important for our process nucleosynthesis in this case is not so much the total mass of the disk, but more sort of the momentary the accretion rate m dot and the density, because they are related, and that is what is important for the weak interactions to change the amount of material. So the point is that regardless of the exact progenitor model that you assume, whenever you get accretion rates that are high enough, you will inevitably form essentially these neutron-rich outflows.
And then how large is this m dot variation from one progenitor to another? Okay,
yeah, that's also a really good question. So typically, at least for the progenitor models that I had available, which are the Heger models, they include progenitors from 20 to 35 solar masses or so. And so you get different accretion histories, but in almost all of the cases, except for one, I believe, you get accretion rates that are high enough to actually power a long gamma burst and also to go through this neutron-rich wind phase. Typically, all these models start at accretion rates at least of a solar mass per second or even higher, which is when they form the black hole, and then sort of gradually decrease as you go to outer to sort of more outer layers. And the only question or the only variation that you actually have is, depending on the progenitor models, is how long that period will be. And the time and the duration of this high accretion rate, so being, say 0.1 solar masses per second or so, or a few in 10 to minus 2 solar masses per second, that duration can actually vary a lot. And that imprints also itself on the duration of the long gamma burst. And there can be a lot of variation in there.
So which translates into the amount of our process?
Yeah, so this is exactly what translates into the total amount of our process. So if I go back to this slide here, this is essentially what gives us in the end, if you look at sort of this 0.3, this is essentially what gives us this broad range of total R process material of between a few and 10 to the minus 2 for those progenitor models that only go through a very brief of this high accretion rates. Up to even a solar mass or so for some stellar model that provide a very long duration of this high m dot phase.
Well, a factor of 100, and we'll see if we can constrain that.
Right.
Any other questions for Daniel?
Daniel?
There is, yeah.
Yeah.
In that factor of 100, is the composition of the R process the same, like the relative ratios of light and heavy stuff?
Yes, so unfortunately, since these simulations are very expensive, we've only run a couple of these simulations at like very selected m dot cases. And so this number essentially assumes that essentially categorizes each fallback or accretion history of a stellar model into these different phases defined as R process, light R process, nickel 56, and helium 4, which are indicated here in this upper left panel. And in each of these sort of segments, I assume that essentially the yield is constant, which of course is an approximation. But looking, for example, at this M1, so m.1 and m.2, if you look at the nucleosynthesis pattern, it's actually fairly similar. So I think in some cases, at least it's a fair assumption. And so assuming that, this is how you get essentially this total estimate, this factor of 100.
Okay, thanks.
Mm-hmm.
All right, let's thanks Daniel, and I will see you guys in 2 weeks, hopefully.